All right, class, here is section 4.6, last section of this chapter. Finally, we're going to put all that knowledge that we've gained on exponential and logarithmic functions to solve exponential and logarithmic equations, and then a few applications. So we're going to start with exponential equations. As you can see, to save some time, I already pre-wrote the problems since that's what we'll be doing, mechanics over and over again. So, what makes an exponential equation exponential? Well, clearly, the fact that the variable has to be in the exponent. That's the difference between an equation that says x squared, where the x is in the base, versus 2 to the power of x, where x is in the exponent. So that right here is an exponential equation. Okay, now this one might be pretty simple because what we're simply thinking about is what exponent, right, do I have to raise the number 2 to in order to get 8? Well, that's easy because even if you think about it, 8 is a 2 to the power of 3. So sure enough, x must equal to 3, yes? So easily thought of, yes, thinking, again, what exponent, right, on 2 will get us an answer of 8. One other way of looking at it, of course, we've learned all chapter long that exponential and logarithmic functions are inverses of each other. So if you look at it, I mean, we have several options, right? Why did this... By the way, why did this 2 go away? Because, well, we simply, I mean, it's obvious, right? 2 to the what is 2 to the third, right? But really, how we remove this 2 here is simply that we have undone the base of 2, and that's to be undone with the log of base 2. So this is how they canceled out. The same way as really anytime you do what? You solve, let's say, a radical equation, right, that you want to solve. How do you remove this square root? Well, you square both sides, right? That's what undoes the square root. Now, let's say this was not a square root, but it was a fourth root. Then what would you have to do to remove this fourth root? Well, you raise it to the fourth power, right? That's what makes it go away. So as long as the indices are the same, they're going to cancel each other out. So the same thing here, a base of 2 and a log with base 2 will undo each other. And sure enough, you've solved problems like this, right? Where you had a radical or square root or a radical of any kind on both sides of the equal, and we just simply said, well, if their square roots are the same, of course they must equal to each other, but technically, really, what did we do? We squared both sides, and that took care of the square roots on both sides, yes? So it's the same idea here, pretty simple. I said we had a second option for this problem. The second option is, remember, this is the exponential form of this equation. We can turn it into a logarithmic form. So this is what you've been practicing in 4.3. So if 2 to the x is equal to 8, that means log with base 2 of 8 is equal to x, right? So rewrite this into a logarithmic form. And then, of course, you have to evaluate the log, right? So if we, by the way, it's going to come up very soon, won't be able to tell what log with base 2 of 8 is, which we know it's a 3 because 8 is an exact power of 2, then this method will definitely help. All right, enough talk about this. There it is. So the question always at first is, can you write both sides of this equation in terms of a common base? In other words, I see here I have a 2 to the 3x plus 1, yes? Can I rewrite 128 as a power of 2 as well? If not, definitely you can turn into a logarithmic form, as I'm going to show you in a bit, and use your calculator. But as it is, 128 is 2 to the 7th power, so again, that makes 3x plus 1 straight equal to 7, yes? And then from here, once we set the exponents equal to each other again, in the background, really what we've done is we logged both sides with the base of 2 to make them go away. It's just a simple linear equation, right? X is equal to 2. Boom, done. Okay. Now, as I said, if you didn't know that 128 is a power of 2, what could you have done? You could have taken this equation and turn it into a logarithmic form. So log with the same base as this one, right, of 2 of 128 is equal to 3x plus 1. So now we just have to figure this part out. But again, it takes recognizing the fact that 128 is 2 to the 7th power. But if you don't know that, what have we learned? And again, we're going to use that in a minute when we won't have a power of 2 inside that log. So we've learned the change of base formula. So all you have to do is to evaluate it using your calculator, right? Log with base 2 of 128 is natural log of 128 divided by natural log of 2. So if you put that in your calculator, you will get your 7, right? And then you'll continue from there. So either way, this can easily be done. Okay, let's try this problem here. Maybe not such a high power of 2, right? We can figure out 2, 4, 8, right? Keep multiplying by 2s. At some point, we might get bored of it. So 4 to the x is equal to 32 to the 3x minus 1. All right. So what do I see when I look at this equation? I see that I have variables on both sides. That's great. So again, what I'm thinking about is, can I rewrite these numbers as powers of a common base? In other words, are 4 and 30, because 32 is not a power of 4, right? It's 4 times 4 is 16, 16 times another 4, it gets you to 64. So that's not going to be it. So what we're going to try and do is rewrite both these bases, if we can, in terms of a common base. And they're both powers of 2. Okay? So, of course, we know that 4 is 2 squared, and 32 is a 2 to the 5th power. Okay, so the rules of exponents say if you have a number raised to an exponent to another exponent, you get to multiply the exponents. And the same thing here, be careful. This 5 gets to be multiplied to both 3x minus 1, right? All right, and we're back in business. The bases are the same. They will just cancel out. I might as well distribute already. So that's a 15x minus 5, right? So the exponents, the bases are the same. The exponents have to be the same as well. And there you go. Now it's just a linear equation. So I'm going to minus the 15 over the 15x, and I'll get negative 13x is negative 5. Great. Divide by negative 13. So x is going to equal to 5/13, whatever it is. Doesn't have to come up pretty. All right. Okay. All right, getting the hang of it. So we're using rules of exponents, right? It's an exponential equation. So sure enough, this is the stuff that we need to be ready with. Okay, here it is. 1/3 to the x plus 5 is equal to 27 to the power of x. So same thing. If we could rewrite these numbers in terms of a common base, that'd be awesome. So what is a common base for 1/3 and 27? Sure enough, they're both powers of 3. 1/3 is a 3 to a negative 1 exponent, right? That's what made it go in the denominator. And 27 is a 3 cubed. So same as we did in the last problem. We're going to simply multiply these exponents. Again, it's one of our rules of exponents. And there we have it. Again, how does the 3 really go away? You don't have to write this down. But this is really what happened. We logged both sides with a base of 3, right? And that's what made the 3's cancel out. So negative x minus 5 is equal to 3x. And now it's a super easy linear equation. I'm going to add the x over for a total of 4x, right? Don't mess up on the little stuff. Divide both sides by 4. So x equals to negative 5 over 4. Done. All right. Ooh, same thing. 3, 3, and 9, which is a base of 3 as well. So let's rewrite this. But this is the first time we see something like this. Now, is there another maybe rule of exponents that would allow us to put these together? So yes, and again, remember we just reviewed the rules of exponents in the beginning of 4.5. So it says if you multiply numbers with the same base, what you're going to have to do is you get to add up their exponents. Okay? All right. And the same thing here, 9, well, not the same thing, but 9 should be rewritten as a base of 3. That's a 3 squared. So I have a 3 to the, by the way, 3x plus 1 is equal to 3 to the power of 10x. There you go. Again, multiply the exponents. When you multiply numbers with a common base, right? You don't multiply the bases, right? What this tells you is these are a bunch of 3's multiplied together times some more 3's that makes a total of this many 3 factors, right? So add up the exponents. Good. Drop the bases. 3x plus 1 is equal to 10x. 7x is equal to 1. Divide by 7, and there you have it. X is 1/7. Boom, done. Okay. All right. And let's move on. This one's tricky. Why? 7 is not a power of 2. No matter how much you think about it, you can rewrite it as a 2 to some kind of exponent, like we did right here, right? 8, yes, is a 2 cubed, but 7's just close of that. So if anything, we possibly guess that the answer is going to be a little bit less than 3, because 2 to the third gets you 8, so 2 to the something less than 3 will get you as far as 7, right? But since that's the only way, and again, I could solve this problem for you again 2 different ways. One way is to rewrite this into a logarithmic format. And what's the logarithmic format of this? Again, is log with base 2 of 7 is equal to x. And look at that, we solve for x. If anything, sometimes you might be asked to find the exact solution. This is the exact solution because as soon as you use your calculator to evaluate it, you will only just get close to the answer, but not exactly on it. But how are we going to find the approximation of it? Again, use a change of base formula. So we learned that log with base 2 of 7 is equal to natural log of 7 divided by natural log of 2. So when you put this in your calculator, which I'm doing right now, divided by ln of 2, it's going to get you 2.8074-ish. Okay, and again, this is just an approximation. Right up here would be your exact answer, which is kind of nice. That means you don't actually even have to use your calculator or know the change of base formula. And this is your approximation. Okay, now of course you're going to ask me, which one do I want? I want you to give me the approximation because I want to see that you can figure out that number. Okay. Now, how else could I have solved this equation? Well, again, I need to get in here to x, so I need to remove this base of 2. So that's what needs to be removed in order to get to x. So how do I remove a base of 2? Well, I'm using a log with base 2. So this log with base 2 will cancel out the base 2, and will leave you with x equaling to log with base 2 of 7, which is, of course, the same exact answer we got above. So if you do not know, by the way, it looks like the switching from exponential to logarithmic form, you can always just log both sides and you end up in the same exact spot. So sure enough, again, it's the same story, right? We'll use a change of base formula. I'm going to squish it, but of course it's the same answer, right? It's the same problem. All right. Okay, so let's move on to more exponential equations. Okay, so same thing here. 3 to the x plus 1 is equal to 57. And sure enough, 57 is not a power of 3. So what are we going to do? Again, whichever one you prefer, log both sides, right? You want to get rid of the base of 3. So I'm going to log a base of 3 on both sides. So x plus 1 is going to simply equal to log with base 3 or a 57. Or, as I said, simply change your the exponential form into a logarithmic form. And again, to get to x, all I have to do is subtract 1 from that side. So again, this is an exact answer. The approximation for this is us using the change of base formula to figure this answer out. So I figure I might as well, looks like you could see it. So my calculator, I'm going to simply put ln of 57 divided by ln of 3, and I'm just going to make sure that I'm getting the correct answer. In other words, don't put the -1. I can just simply press enter. You can -1 in your head, or just now say answer -1, and there you go. The answer is about 2.68. Now, normally when we give, excuse me, decimal answers, we like to use 4 decimal places, but 2 are perfectly fine as well. Okay, now it's getting even worse because look at this. I have, the x's now on both sides. This was pretty enough, okay, but now the x's are on both sides, and both 2 and 11, they don't have a common base, right? So I can't rewrite them as 11 is not a power of 2. So how can I solve this problem? Again, you can't, I mean, the nice thing is here we just had the x's in one exponent, so I logged it with a base of 3. So now what am I going to do? Log it with a base of 2, log it with a base of 11, or what should I be doing? Well, I'm going to tell, you could do either one. By the way, you can just use a log with base 2, at least this one's gone. Or you can use a log with base 11, at least that one's gone. But I'm going to make this even faster. On the last 2 problems, when the equations did not have a common base on both sides, right? Like problems 1 through 5, right? We could rewrite these as a common base, right? So there's a 3 on both sides, we could just drop the bases, right? Or a 2 on both sides, we could just drop the bases. But the last 2 problems we didn't have this luxury. So what did we have to do in the end? We had to use either the natural log or, by the way, the common log to put this in the calculator. So either way, you're going to have to use that natural log to solve this problem, right? So best thing would be use it from the beginning. So what I'm going to do is I'm going to apply a natural log on both sides of this equation. Now, what does that do? So let me rewrite it for you one more time. This is what I have now. ln of 2 to the x plus 5 is equal to ln of 11 to the x. Now, this doesn't seem to be looking all that good, except for finally, we get to make use of those properties of logs. That said, if you have inside a log a number with an exponent, what can we do with that exponent? We can take that exponent up front. Okay. And then the same thing here, there's an 11 with a power of x. So that x gets to be thrown up front, and there you have it. So we're back to a linear equation. Now, how do we solve this? Best thing would be if I wouldn't see ln of 2 and ln of 11, because again, I want an approximation. Okay, so again, I'm just going to rewrite these. What's ln of 2? Well, the answer is ln of 2 is equal to 0.6931. And ln of 11 is a 2.3979. 3979. All right, there you go. So as you see, this is now back to a linear equation. So 0.6931x plus 0.6931 times 5, which is 3.4655, is equal to 2.3979x. And again, if you want to make it simpler, you can definitely just use 2 decimal places. So it's a linear equation. I'm going to get the variables to one side, keep the constants to the other side. .3979 minus 0.6931, that's a 1.7048x, and of course, what's the last step? Divide by this 1.7048. And then x will easily, not so much room, but there you go. X is about a 2.038. 328, sorry. There you go. Okay. So again, using 2 decimal places surely would have gotten us at least faster, because we at least wouldn't have had to write so much. Okay. All right, this one looks pretty nice again, because as you see, the x's are in the power only of this one number. And by the way, what's that one number? That's the Euler number, right? E. Okay. So definitely, what should we do first? We should simply add the 5 over, right? Okay. Now, how do I get this number out of the exponent? Well, we should maybe log both sides, right? I want to get rid of that base of e. I need to log it. And what is the log with base e? And if you've said ln, then you would be completely correct. So the natural log takes care of the natural exponential function. They're going to cancel each other out. So now when you're putting an ln, let me just show you what my calculator's telling me, of -90, domain error. What does that mean? Why doesn't it want to give me an answer? It doesn't want to give me an answer because it doesn't want to give me an answer because if you remember, the exponential function only ever gets positive values. The exponential function will never be found below the x-axis unless, of course, you shift it down. But an exponential function, e to the whatever, right? That's what exponential functions look like. Their range is 0 to infinity. So it's not going to be down here in the -90s. Another thing we've learned is that what? You're not allowed to put negative numbers inside the log, right? Again, no solution for that. So that's why it's a domain error, because you threw a negative number inside the log and the calculator knows not to like that. Okay. All right. So that being said, we are learning that exponential expressions better not turn up negative. This one might be better. So same thing, what am I going to do before I even get to this exponent? I could definitely clean up the e, right? Minus the 6 first. Then what else? I can even remove this 3 that e is multiplied to. I can divide it. And now finally, and again, unfortunately, it's not as easy as equaling to a negative, so that means we have to move on and we'll get an answer. So how do I get rid of e? I'm going to undo it with the log of the same base, which is the natural log. So these cancel out. 3 minus 3x, remember the properties of in 4.5, right? Also, I wrote these things down, that an ln and an e cancel each other out because they're inverses of each other. So what is ln of 7? That's going to be a 1.9459. And then it's now a linear equation. What do? I'll minus the 3 from both sides and get a negative 1.0541. And then what? Divide by negative 3. And I'm going to get that x is a 0.3514-ish. Again, 4 decimal places is plenty. And I'm even going to put an approximation, right? As soon as we use that log, we had to cut it short, right? How short? Well, 4 decimal places, that's what we gave it. All right. Now, these last 2 equations here are super fancy and a little bit tricky because, I don't just have nicely one exponential expression, right, that I'm going to hunt for, or find 2, but 1 on each side. I have 2 of them, but then there's an extra number, so either way, it's not just going to be, well, ln both sides and those e's are going to go away. That's not true. You cannot distribute a log to a somewhere different, so don't be thinking of that. However, last 2 equations have a specific format. So if you think about it, you see this trinomial, right? And then you see something with the x and then another e to the x. And what you're noticing is that this exponent here is twice as much as the exponent in the middle. The same thing happens here. So both of these is what we would call quadratic type of equations, and we will solve them by factoring. So again, as I said, what you need to be noticing and what has to happen, and we've had these problems in chapter 3 as well when we solve those polynomial equations, and I said write an x to the 4th and then in the middle an x squared. So I said what's important is that the exponent at the front has to be twice as much as the exponent in the middle. So that makes it the square of this guy here. So in other words, this is your x, and all you have to do is factor it. So e to the x squared comes from an e to the x times another e to the x, right? And that makes, when you multiply them, it's an e to the x plus x is your 2x, right? And then I'm thinking of numbers to multiply to 6 and subtract to be 1, which are 3 and 2, a negative 3 and a positive 2. And perfect, that's it. So it's just simply like you would have factored out the same thing as an x squared minus x minus 6 equals to 0, right? That's the same exact type of equation. It's a quadratic type of equation, except for your x is not x, it's e to the x. So what are my 2 options? Now I can use the 0 product rule, and they say that e to the x is either 3 or e to the x is negative 2, right? Set them equal to 0. And then move these numbers over. So now we've turned them into simple linear, into simple exponential equations. I'm going to log both sides. So x is going to be ln of 3, which is some sort of a number. And while I do ln of 3, it's 1.0986. And then e to the x is negative 2. Again, when you log both sides, what's going to happen? X is ln of negative 2? I don't think so. And you could have stopped right here as well. As we just talked about, exponential functions do not get to be negatives. They don't even get to equal to 0, right? They have to stay strictly above the x-axis. So, but if you put in a calculator and end up with an ln of negative 2, your calculator at least would stop you. Okay, And here's another one. I have a 10 to the 2x minus 5 times 10 to the x minus 14. So again, what this is your actual x, right? So again, it's like having an x squared minus 5x minus 14 type of an equation, right? Maybe I shouldn't have used x, maybe I should have used u for substitution. I usually like to use u for substitutions, or a y or something else, but again, I'm not going to even do that. I'm going to, factor this. I'm going to simply straight up factor this trinomial here. Who is my x? 10 to the x. In other words, that's your variable part, right, at the front. And then again, looking for numbers that multiply to 14 and subtract to be 5, and these are easily 7 and 2, a negative 7 and a positive 2, yes, add up to a negative 5, and multiply to a negative 14. And again, welcome to try and distribute all this. You get a 10 to the x plus x is 2x, minus 7 10 to the x, plus 2 10 to the x, which combines to negative 5 of them, and then the negative 14 at the end. So 10 to the x is either 7 or 10 to the x is negative 2. And again, this is not going to work. Why not? Exponential functions do not turn negative. What would be the most appropriate log to use to get rid of a base 10? And if you said the common log, you would be correct, because the common log has a base of 10. So x is the common log of 7. Good news is we have a button for this on our calculator. There it is, common log of 7. And that's a 0.845 something. 0.8451-ish, 4 decimal places. There you have it. All right. So that's enough on exponential equations. This is a good practice. We're going to continue this with logarithmic equations.